Alright, welcome back to derivatives. The last time we talked about derivatives, we were taking derivatives at a specific point. The derivative at a specific point is telling you what the rate of change is at your point. And so if you think of your function in terms of distance, the rate of change is speed. And so when you think about taking the derivative, you're kind of thinking of asking what is the speed of the function changing as we move along it. Now, we saw how to compute f prime of a, and remember f prime of a is a notation we use for the derivative. And we're taking the derivative at a point for x equals a. And that's nice, but what we want is we want to be able to take it everywhere. And so what we want is we want a function f prime of x such that for all a, f prime of a agrees with the previous definition. So we want to be able to compute the function in terms of x so we can plug in all the values we want. And so the way that that works out is that we want f prime of x to be the limit as h approaches 0 of f of x plus h minus f of x all over h. You see, the only difference in the definition here and the one we had before is that we're just using the variable x as opposed to one of our numbers. And so f prime of x is just a function then, right? We can plug in lots of x's for it, and the question is, what can we say about this function? Well, f prime of x is only going to make sense when that limit makes sense. That limit can only make sense if we can plug in the values of x, which means that we have to be able to plug in f of x. So as a domain, it has the same domain as f of x, except every time that that limit doesn't exist. And so it's totally possible for the limit not to exist, and so we have to throw out some extra points. F prime of x computes the slope of the tangent line to f of x for all x in the domain. So the point of f prime is it gives us the slope of the tangent line for the points on the original function. F prime of x equals 0 whenever f of x has a horizontal tangent line. What does it mean to have slope equal to 0? It means that you're horizontal. If the limit as x approaches a of f prime of x is plus or minus infinity, if the derivative goes to positive or negative infinity, then we have a vertical tangent line. And f prime of a cannot exist when f of a does not exist. And that's actually just reiterating what I said up in the top about the domain. So let's go ahead and compute a couple of derivatives. And we're going to use a couple of really easy basic functions, and then you're going to go ahead in the homework and compute the derivative for some slightly more complicated functions. So let's look at the constant function, f of x equal to c. Well, by definition, f prime is the limit as h goes to 0 of f of x plus h minus f of x all over h. And if we just plug in everything, we're going to see that both of those functions become c. And so we get the limit as h goes to 0 of c minus c over h, which is the limit as h goes to 0 of 0 over h. Now, if you're thinking for a second that this looks a lot like 0 over 0, it's true, except whenever h isn't 0, 0 divided by anything is 0. So it's equivalent to the limit as h goes to 0 of 0, and we saw that the limit of a constant is just whatever the constant is, so the limit of 0 as h goes to 0 is just 0. And so f prime of x is 0 when f of x is c. The identity function. So the identity function is one of the more basic functions. It's f of x equals x. Whatever you plug in is what you get out. F of 2 is 2, f of 5 is 5, f of x squared is x squared. And so let's take the derivative of the identity function. The derivative of the identity function is f prime of x. Its limit as h goes to 0 of f of x plus h minus f of x over h. And if you go ahead and plug everything in, we get x plus h minus x over h, which is h over h. And again, h over h feels like we're going to 0 over 0, except at any point other than 0, h over h is just 1. So we can replace the limit with the limit as h goes to 0 of 1, which is 1, for the same reason that the previous limit was 0. And so the derivative of the identity function, f prime of x, is 1 for f of x equals x. And so we just dealt with a couple examples of linear functions. Linear functions are just lines. And if you have a line, the slope of the line, right, the slope of the tangent line is the same thing as the slope of the line. A line is its own tangent line. Here's a couple of pictures of two lines. And the left one is constant, so the derivative is 0. The slope of that line is 0. And if the right function is written as f of x equals mx plus b, then the slope is going to be m. Now here we have a picture of a curvy function, and the derivative for a curvy function is not going to be constant. You can see a couple of things. That whenever the function increases, which is now the brown part of the function, wherever the function increases, the slopes are positive. The tangent lines are going to be going up and to the right. And where they're negative, the function is decreasing. The tangent lines are going to go down and to the right. And that's really it. So whenever you have a curve, you'll have a more interesting function as your derivative. And if you have a straight line, you'll have a constant number as your derivative. Now, what you're going to do is you're going to compute a bunch of different derivatives for different functions, and you're going to come up with the rule for the derivative for that function. The next video we're going to have will give us a bunch of rules that we can use to make computing the derivatives easier, but in the meanwhile, put in the work, understand the derivative, and I'll talk to you later.